Carrying on our lecture on confidence intervals, we're now going to do things backwards. So earlier on in chapter 9, what we did was look at some data that we just collected and then determine how reliable the answer was. And we did that by finding standard errors, margins of errors, and confidence intervals. Now we're going to flip this all on its head and think about what happens before we gather the data. So one of the most common questions that I always get is, how large of a sample size do I need? And the answer is, it depends. All right, so it really depends on three things. So what is the acceptable margin of error? Then how confident do you want to be in the results? So in practice, this confidence level is almost always 95%, which means that we're always using a z-value of 1.96 or 2. And then the third thing it depends on is how heterogeneous is the population, as measured by the variance of x, the population variance. Okay, now if that's the case, if we know these three things, then the sample size you need is simply z squared sigma squared over e squared. Now how do you get this? Well, if you remember, the margin of error is just the z-value times the sigma over root n. We solve this for n and we get this formula. Okay, well, let's go do a problem. The transit system of some major metropolitan area wants to determine the average number of miles a commuter drives to work. Past studies have shown that the variation in commuting time is 5 miles. So that's our sigma. Managers want to be 95% confident. So there's our confidence level. This means that we're going to be using a z-value of 1.96. And they don't want the error to exceed 3/4 of a mile. So that's our E. So with these three numbers established, we just go drop them into our formula. And we learn that we need a sample of 170. You should probably check this. Okay, so that's the new piece. Now let's move on. And part 2 brings us back to the beginning of chapter 9. So now we've done our survey of 170, and the results show that commuters drive an average of 20 miles. So this average of 20 miles indicates that x bar is 20. And we find that the standard deviation from the sample is 10. So that's our S. Find a 95% confidence interval. So 20 plus or minus 1.96 times 10 over root 170. And we get a confidence interval of 20 plus or minus 1.5. Now note, we've missed our goal. So we were shooting for a confidence interval with a margin of error of 3/4 of a mile. The margin of error was 1.5 miles. So what went wrong? Well, the thing that went wrong is this standard deviation. So we budgeted for a population standard deviation of 5, but it turned out the population was a lot more heterogeneous than we thought, and that's why the confidence interval is twice as wide as it should have been. Let's go on to part 3. In part 3, we've done our sample with 170, find the average to be 20, and this time the sample standard deviation comes in at 5 miles. So find the 95% confidence interval. We'll notice we get exactly what we asked for up above, which was a margin of error of 3/4 of a mile. So the moral here is that these formulas are as good as the numbers that you put into them. So if you put in a rubbish estimate of the standard deviation, the margin of error is going to be incorrect. What should we have done back in part 2? Well, we'd have to gather more sample. So if the true population standard deviation is 10, then we're going to need a sample that's much larger than 170. We go pop that into the formula up here. In fact, why don't we go do that just to show you how it's done. Do this in Excel. Let's make it a little bit bigger. So if we were to take z squared, so 1.96 squared times sigma squared, so 10 squared, divide by 0.75 is the standard error that we were after. So we're going to need a sample of about 683. We already have a sample of 170, so we'd have to get another 510 or so. All right, well, where do we get these estimates of sigma squared? You can get them from a number of places. In this problem we just went through, we had an estimate from a previous study, and we saw how maybe that previous study is right, but not always. If you don't have a previous study, you can field a pilot survey. So if you could go interview, say, 20 people, that would give you an estimate of the standard deviation that would probably get you in the ballpark at least. Sometimes you can find a secondary data set where you get data from Nielsen or you get data from the US government that would put you in the ballpark. Judgment just means that you're pulling a number out of the air. With rating scales, there's a reading in the course packet where I give some typical standard deviations that you see from Likert scales and semantic differential scales. These are the things that have 5 or 7 points. Finally, if you have a normal random variable, one way that will get you into the ballpark is by taking 1/6 the range. So sometimes you can make a stab at what the range is. So why 1/6 the range? Well, let's go back to our empirical rule. What the empirical rule tells us is that 99.7% of the distribution falls within 6 standard deviations, with 3 standard deviations either side of the mean. All right, so if you can guess the min and the max, so let's say the min were something like 10 and the max was 70, then the range is going to be 60, which is 70 minus 10 is 60. And so therefore sigma we would estimate as being 1/6 of that, which would be 10. All right, so that's another commonly used approach. For proportions, remember that the variance of a Bernoulli trial is pi times 1 minus pi. Now let's go draw that. Here is pi, and here is pi times 1 minus pi, which is the variance of a Bernoulli trial. If you plot this out, what you get is a parabola. And that parabola achieves a maximum value at a pi of 0.5. So what that means is that the most dispersed a population can be is when it's 50-50. So that should make a certain amount of sense. If you had, say, 90 women in a room and 10 men, that's certainly more homogeneous than having 50 men and 50 women in that room. Okay, so if the most mixed it can ever be is when it's 50-50, then the population variance is 0.25. So the population variance will never be any worse than 0.25, and that's what this is saying. So, if you know nothing else and you're estimating a proportion, drop in 0.25 as the standard deviation, as the variance, pardon me. And so that's what the second bullet means. If you have additional information where you, for example, know that that proportion would never exceed, say, 0.2, well, if that's the case, then the variance would never exceed 0.2 times 1 minus 0.2, which is 0.8. So 0.16 would be your estimate of the variance if you knew that the proportion would never exceed 0.2. Well, let's do a few problems. A pollster wants to estimate the fraction of people who vote for some candidate. The maximum error should not be greater than 5% at the 95% level. How large of a sample should there be? Well, recalling what I just said about proportions, if we know nothing else about this election, drop in 0.5 as your pi, or 0.25 as the variance. And what you find is that you need a sample of about 384. Now that 384 is roughly 400. So I would remember the number 400. If you have a sample of 400 and you're estimating a proportion, then the worst case margin of error is 5%. That's just a good number to remember. Here's a few other numbers. If I'd asked you to find the sample size you need to achieve a 3% margin of error, well, you'd need a sample of about 1,000. And if I asked you to find a margin of error 10%, you need a sample of about 100. So I'd recommend memorizing those numbers, 400, 1,000, and 100. gives you margins of error 5%, 3%, and 10%. So it's amazing how often these things come up in a meeting, and you don't know the margin of error. Somebody wants to know the margin of error. If you have these memorized, you'll you won't have to compute them. Okay, we will now do some problems. I think I will do this in a